As you may know, some of the members of our congregations are working at CERN. And also this Advent, we are using physics as a parable to retell some of the concept of the Advent story. Last week, Greg explained why the Higgs boson that we found at the LEC this year is so important for modern particle physics and a cornerpiece of our giant physics puzzle. Of all the new particles that have been found during the last 50 years, the Higgs is one of the rarest, most important, most elusive, and hardest to find elementary particles. The question is, how hard and why is it so hard to find the Higgs? In physics, we often like to express our findings in numbers or probabilities, but particularly for high-energy physics, these numbers are often too large or too small to comprehend, that I thought I'd give more visual representation of this. Some 10,000 years. One tiger, one man, and the ability to detect the tiger hidden in the reeds made the difference between life and death. This might sound strange, but this is very similar to what we're doing at CERN for finding very rare particles in front of a very hard-to-see background. Can you see the tiger? I hope. Good. That's an easy task. So you should, because 10,000 years ago that means you're dead or alive. Now, for particle physics, conceptually the idea of modern particle physics is very old and very ancient. The Greek believed that everything we and things around us can be made out of matter, consists essentially of fundamental building blocks. They believed there were four: fire, wind, air. Perfect. And basically this view was kept for 4,000 years with a small addition of elements. The chemists found about 100 though of an addition. This whole view was shattered when people found that these atoms, as they were called, because the Greek believed that you can't split them, but the world was shattered when people saw that these elementary blocks, the elements of the atoms, are not fundamental, but you can split them even further into electrons, cores, lots of space in between, and further even the core could be split into smaller and smaller parts, which we now refer to as quarks. Quarks are the fundamental building blocks of matter, and were discovered in the late 60s by a fairly small group of people consisting of tens of scientists. So where the elements usually required one person working hard, isolated, now looking for the smaller particles, we need 10. Further particle searches required a number of people that even increased about 10 times every decade, and despite the more and more people working on this problem, the time it took to discover the particles doubled. So, for example, during the early years of the 80s, we found new particles that explain why the sun burns hydrogen and why we have the sun shining upon us every day. And these groups increased. Not 10 anymore, but beginning of the 80s, we had about 100 researchers and scientists looking for this. A decade later, the heaviest particle found at an accelerator nearby Chicago. And here in Geneva, physicists discovered that the particles that make up matter come in a set of 3 families. That was important because 3 families that also concluded how many more particles are there to be found. So by the end of the 90s, we found most of them, and there was just one left, like a corner piece, where people predicted that has to be there. And that was what we now believe is the Higgs boson, which we now believe to have found. Personally, I started studying high-energy physics during the last years of lab, which is the predecessor of the LEC accelerator we operate at CERN. And during these times, the researchers weren't small groups anymore, but large, very large collaborations of thousands of scientists. So to know everyone by name was very difficult. We have about 100 people in this church, and to find that we have a limited number of particles, thousands. Now, 1,000 is also the number where most lose the more physical connection of being able to count, and where numbers become more abstract and more of a mathematical construct. And the probability to find something new within the duration of one PhD thesis, which was important at that time for me, was very slim. So most hoped, or at least silently on the back of the head, let it be during my time of PhD that we find these new particles, because otherwise you have to wait for another 10 years, not good. And this fight, the incitement and eagerness, we have to find something, in particular to get a PhD. Especially the last day of lab, when we stopped operating, there were lots of people saying could that be a Higgs? Maybe the Higgs is just around the corner, just leave it running, just a day more. We just have to find, and then it's to be there. What does it take to find the Higgs? Now, the modern experiment, the size of the Atlas, CMS, and other experiment at CERN exceed 10,000 of scientists and engineers looking for one particle. And these people are needed to operate this very complex scientific apparatus. And now the numbers become a bit large, and I brought a friend along. He's coming from Australia, Mark. Please come, give me a hand. And he's helping us at CERN to help with research. And can you send him a right? I'll draft you later. So that's about what we had. So now we're coming back to the present era. We need like 10,000 people. If you looking for the needle in the haystack, that is like about 1 in 100,000. If you know that the needle is magnetic, then you use a very strong magnetic magnet, and then the search for a needle in a haystack becomes nearly trivial compared to the Higgs. Now, if you look like for the next number, this is like 1 million. We'd love to have that in our bank account, don't we? In a high-energy physics context, this is a small number, as the Atlas and CMS experiments are use millions of detector channels to precisely measure even the rarest event. Basically, these detectors are very fast digital cameras, taking about 40 million pictures per second, and measure the energy of those particles. Now, 1 trillion, that becomes, okay, that's like with 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, so it's large. 1 trillion. That's a number where even like physicists don't, okay, trillion you still know, but then we start just counting the zeros. And this number is needed to accumulate enough data or volume of the haystack to have a chance to see the Higgs. So we have just that many particles, the probability to see the Higgs is practically 0. So you need more. And to put this number into context, if you buy a new computer this year for Christmas, it probably has like a 1 terabyte or 1,000 gigabyte hard drive. The hard drives that are needed by these experiments to write down the data is 20,000 times that what you have at home. And this is needed, and still it's hard to find it. Now, what is the probability to find a Higgs? How many collisions do you have to do? A lot. And that is, it's about 1 with 15 zeros. That is just to have, that you know that you found a new boson. To make sure that that it's the Higgs boson, you need like another factor 3 of this. So it's very large. This search bore also a lot of risks because the human mind is too easily fooled when searching for something very hard, and that it make itself believe to see facts. So I'm competing. The search is very hard, and the human mind is easily fooled to believe, to find things or find patterns where there aren't any. And this is too human, because some 10,000 years ago, to see some signature of a tiger, even if there were any, it's safer to run away even if there's not a tiger. This is one of the reasons why physics deploys mathematics and statistics, to minimize that we find something false, what is not real there. This goes even to that far that before the summer this year, scientists have been explicitly instructed, don't look for the Higgs. Make sure that you look on the regions outside to make sure that you understand your environment before you're trying to find a tiger in the reeds, to prevent any false, positive or non-scientific conclusions. Finding the Higgs became a truly global effort, and each and every one of us is proud, having seen how hard it is to achieve this challenging goal, that we could witness and do our part in this great discovery. Thanks.